I'll put it now. Alarm 11:40. Okay. So we were not able to finish, and I don't want to run, but we shouldn't spend so much time. So we will, this is a plan for this week. And we were like halfway on the science of structures, which I saw you all passionate about it. The activity showed that your self-appreciation of your understanding was a bit optimistic, which is the usual. It was not too terrible, but actually shear stress concept, which is important, is misunderstood by almost totality, the same as the Young modulus. We don't have time today. Let's go on, and I will upload in Blackboard the activities with the comments, and we may comment next week. Today we try to catch up so we don't accumulate materials from last week. Remember, we were in this, and this is something you all understand, right? The bending and how things crack, so I will not insist on it. And this is a thing that kind of confuses people. Let's go the shear collapse, right? Which also happens. And we have to try to make our mindset about understanding the principles, not memorizing the graphs you have in your head. Still, everybody is doing the activity we did with just a concentrated load, as if it was a continuous load, because you have in your memory those graphs and those moments and so on. And this is not the point, right? The point is to understand the principles. And this is obviously one point in which the shear crack happens at the end near the support. That means probably the load is continuous and the most stress is in the support, where most of you did. One load which is in one point, the shear is the same in all the sides. So the crack may appear anywhere in the beam, right? So if we make well, this is just the as it is now, but probably the beam was supported in two sides, right? And with a continuous load. In that case, the graph of the shear is like this. So the strongest stress is near the support. This is why the crack happens there, and how you draw it. But actually, we should change the color. We had a concentrated load. So the graph is more simple, right? That means the stress is the same everywhere. You may have cracks anywhere, because it is exactly the same stress all along, right? That's very easy to understand, and it's better. I prefer you get the concept idea of what is a shear and how it happens than memorizing those graphs that by themselves are not so meaningful, okay? So let's continue. So this is the summary of what we saw yesterday. The most basic we need to know about the materials for structure is the strength. I'm used to kilograms per square centimeter because it's very intuitive, right? It's very old. We all understand 1 kilogram and 1 centimeter. Nobody understands 1 megapascal, right? It's a very abstract unit, but okay, this is what we use now. The yield limit, elastic limit, you know, we used in engineering, we use both like the same thing. It's not exactly the same, but elastic limit is usually what we say when we say this steel is 400 megapascal, right? We are telling the elastic limit. This is also the strength we will use to calculate. We don't use the breaking point. And then the degree of elasticity of stiffness is what tells us not when the material will break, but how much it will deform under stress. We recommended materials, and well, I saw the videos last year, and we had a bit more time. We have aluminum, some alloys as strong as steel. Why don't you use it? Because if we have the Young modulus, if steel is like this, right? Aluminum is like this, and breaks earlier. So it is very close to strength, right? This is aluminum. This is some alloy, not aluminum, right? But the deformation will be much more than we could accept in a building. This is why the use is very limited, right? This is the point. And this is why the Young modulus is important. And somebody asked an interesting question. There's a relation between strength and Young modulus. Not necessarily. Well, some material still is strong and stiff, right? But we had example the other day. We have the neoprene. Let's change the color again. Neoprene, which was the correct answer, but maybe only 20% of people got it right. Neoprene may break at the same tension as concrete, as good concrete, right? But it's very, very soft. So it will break at very high stress. But the formation is totally useless to make in a column or in a beam, right? But it is great to use in supports, in connections where they are very small and they can absorb vibrations and so on. So you can have a ion modulus and strength in all possible variations. You have very strong materials, very stiff, brittle materials, very soft. Soft materials, very stiff, but okay, they are not strong, right? One typical example is a cookie, cookie, the ones we eat, right? Cookies are very soft, but they cannot deform, they break, right? That means they are stiff. Of course, they cannot compete with steel, but in concept, this is something which is stiff. If you have a muffin or donuts, right? Maybe you break with the same strength, but they will deform, right? So they are both soft and have a very low ion modulus in relative terms, right? To show the cookie and the donuts, we should enlarge a little bit of the graph, and then we do have the cookie, right? And the donuts having a lot of deformation before we are able to break it, right? So they are not correlated. They can be in any combination. I hope you understand it, because this is a great exam question. So this is a summary of the tensions, right? We have longitudinal tensions, those that happen in the length of the material, and tension and compression are the easiest. And this is why you all understand you have to put a longitudinal bar to support the moments, right? This is longitudinal. But we have the transversal, right? And transversal is the shear. Well, this is just the movement, right? Actually, moment is tension and compression normal. So this should be probably over there. But this happens in this section. Then we have torsion. We didn't comment about it because it's not the most common, but still engineers have to deal with it. This is what happens, right? And the effect will be similar to shear stress. So you will have a diagonal cracks. If you imagine how it forms, you will understand the cracks logic. And since this is rotating, all the tensions will be accumulated on the exterior, right? This is just because you have more moment. So in concrete, we will have like a lot of reinforcement just in the skin of the element. And this happens very often in the usual structures we have here in Korea, right? The beams over girders, in which one deformation makes the sides to bend and have this kind of torsion. Fortunately, engineers deal with it, not always. So very often they just trust the safety margin, and I think that's a mistake. Calculating time, and no matter how much it takes, is cheaper than repairing later. But well, it is important you're aware that exists. And if you plan your structures, or you work with them, or you just work in an office in which you have to draw those things, which happens very often, it's nice you understand it, because you might avoid mistakes of you drawing, or you might spot mistakes of other people overlooking that. So now we are familiar with elasticity, right? We went very fast, but the very, very basic principles, if you understand that, you can understand most structures, right? And how they are planned and calculated now. So some tips. First is from the everyday elements, beams. And what is in the drawing is the usual beam, right? Like somewhere between 1/10 the height of the length, about 1/13, right? This is the typical proportion of beams, right? This is the drawing. With a continuous load, which is also the most typical case. So we know that the shear is a function of the length. Moment is the square of the length, right? And deflection is the fourth power for this case. This is interesting. If you make the formula, it happens like that. So this happens because moment can be calculated as an integer, right? As an integer of the shear, and deflection is an integer of the moment. Should be the third power, but well, it happens to be like that. So that means that in the usual range, usually the moment will be the critical thing, right? But in very long elements, even if the moment is resisted, deflection becomes critical. And in very short elements, moment and deflection are insignificant, and probably the failure will come by shear. This is something we understood after some earthquakes in the 1980s and 90s. So when you pre-dimension, you may have, your dimensions of your building, and you may plan where you put the main structures, the main spans, or how do you add or remove the columns to make the spaces better. So just to apply this, we may have this is activity. So those online, you can do on your sheet. I think you need just 2 minutes. We have a 4-meter beam, very common beam. We don't worry about the final numbers, but we will just enlarge to 6 meters. This is 50% longer, right? So we'll make a fast calculation, and the numbers are very simple because 4 and 6 are very easy to calculate with. You don't need calculator, just your mind. How will change the shear, the moment, and the deflection related to the initial state with the same load, only changing that distance. Can you do it? Do you understand the question? This is favorite exam question. So we have one beam with a load, continuous load, right? The same in the example before. So we have a beam, it is 4 meters with a load, whichever. And we change it to 6 meters because some reasons of design, whatever, right? How does it affect each of the shear, bending moment, and deflection, right? Just the proportion, how much bigger it becomes, because it will become bigger. Moment is very exact, very fast calculation. The maximum deflection is almost exact, so you don't need to worry about the decimal points. Yes, you can speak, you can look online, you can find the last year exams, because we ask this every year, actually. This is very, very easy way to know how things affect the design. And how critical is span definition in terms of structure? Everybody has it? Who finished? Had you already finished? Oh, yeah. Come on, this is 2 minutes. We had all the relations before, right? So we know that the shear is function of the length, moment is function of the square of the length, and deflection is function of the fourth square of the length. So you need only to make the proportions, right? So how much bigger becomes the shear? Yeah, this is, I can do it. Just it's 1.5 bigger, right? What about the moment? Right. Come on, it is square 6 divided by the square of 4, right? Which is 9 divided by 4. By memory is 225, right? We don't need to calculate. Anybody can do by memory 9 divided by 4, right? Deflection is a bit trickier, but you have to go to the square of 225 or just do the calculation. And this will happen about 5, right? 5 is somewhat about 5. Right? Because it is like 81 divided by 16 And now 16 multiplied by 5 is 80, so it's about 5, a bit more. So that means that the length is supercritical in terms of deflection. And this is why in big spans, usually it's not moment what breaks them, it is the deflection. And we'll see some examples of it. However, as we have in this slide, which we come the following, this is Mexico. This is very short columns, right? And they all collapsed by shear. It's very clear diagonal cracks, as we saw yesterday in the center. And this means they had shakes from both sides. So positive and negative, and they will totally collapse. And this kind of shock, this happened in 1986, 87, it's quite advanced. And the engineers thought, against a quake, let's make very rigid buildings. They will absorb all the moments, and that's right. But in short elements, shear stress is critical, and then they collapse that way, right? So this is what we're saying. In very short elements, load is critical, and usually they will collapse by shear stress. It's very hard to make a moment to be critical in a short element. In the typical length, we said like a 1/10 to 1/30 of the length in height, usually the moment is critical, but we have to be careful. If the load is very high, probably we may have shear problems also. And in very long elements, usually the deflection is so brutal that it comes to critical thing. And they usually have a big spans in roofs, in covers, theaters, stadiums. So imagine we have over bending. Well, if the load stops, it will return to the beginning and will not have any problem. But if it rains, if it snows, that will put additional stress there, and it will bend even more, which will have even more overload and eventually collapse, right? And when we say snow and rain, can be also wind, right? So careful with this, because there is not always a moment, as probably your mind has recorded from previous courses. Then we have, well, what we said, we have the creep problem that happens with concrete, with the timber, even more with plastics. Usually it's not a problem unless that becomes critical at some point, right? And this is the case of the excessive deflection. Let's see if the slide refreshes. This is Malaysia, that by no means is a country with poor technology. Malaysia has as good technology as anybody else. And this stadium collapsed twice, which is very embarrassing. 2009 and 2013, it's like yesterday. And one of the problems was the very svelte, very slim structure having too much movement, which created secondary problems, right? In this case, the collapse was by buckling. We will speak about that later. Very strong, very slim elements have a tendency to bend, right? And to buckle, even if they don't reach their maximum stress. So much for elasticity. You can breathe. We went over it. Thanks to Newton and Young, Euler, and all those guys. But we have the strain energy, which is interesting. We will just mention it briefly because I think it's good to be familiar that elasticity is just a 18th century science, right? This is the only contribution of 20th century to the science of structures. And again, as we said, again, this arch is accumulating energy because of the formation. This is what we call strain energy. And if we put it into the construction, this is one of those many new towns, still big chaebol are proud of and make them richer and richer. Those cranes move materials from the ground up. And as they proceed up to 20, 25, 30, 40, 50 floors, there's no limit. And this is all electricity, energy, right? That means that one building is 100% of the time stressed, its own weight plus the loads we put. And this is a big storage of strain energy, right? And when it collapses, that energy is liberated. And that can be huge. In buildings with much stress, remember Twin Towers, the collapse in New York, those towers had steel almost in the limit of stress. They were very, very efficient. When it collapsed, it was like an explosion. And people said, oh, we heard explosions. There were bombs there. Well, it's just the energy accumulated in the building. It's the same as a bomb, right? And of course, that energy is by the formation of the building, right? So this building is not very tall, but it is shrinking under the load, making shorter. So that consideration of the energy allows to explain things that the classical elasticity did not explain. We said in classical elasticity, the moment you have a crack, the structure is failed, but we know it's not failed. And with this, we can deal with the cracks. This is our favorite graph, stress strain equation. So if we go to the plastic period, that area, and we're still with the integral calculation, right? That area is the energy accumulated in a strained element. We have a cold stretched element. We will have another advantage of the cold stretching. They have more energy, much more energy accumulated. That is great because that means that they are more powerful, right? But again, that's scary because they accumulate more energy, the collapse is more catastrophic. But if we go from the beginning, so if we consider the elastic element, but it goes beyond the calculation to one safe plastic part, the energy that accumulates is enormous, right? Cannot be compared up to the breaking point. So, and this is what explains, even though we have some cracks at some point, the structure still can absorb a huge amount of energy before it collapses. And this is very useful for extreme calculations. Not everyday use with people coming in the class or so, but strong typhoon, towers under 100 kilometers per hour or more winds, earthquakes, very special times. This energy might be enough to absorb that huge energy that suddenly comes because of the earthquake and the wind. And we have the tools to calculate it. Fortunately, engineers will do it. Not an engineer. This is quite a bit more complex than the usual elastic calculation, but good engineers, well trained with experience, can work on it, right? Which is quite interesting, I find, right? And this is what we said, right? There is another point. Before computers became a mainstream, computers work with equations of the elastic laws, right? And do very fast and very safe and very efficient. But when we did hand calculations, plastic calculation, what we call, is very easy to do by hand and still safe and much more efficient, right? But computers are not very good at thinking. So now elastic calculation is the norm. But as we said, earthquake, wind, and the evaluation of cracks. And think that in terms of engineering, buildings are like the easiest of problems. Aerospace and naval engineers laugh at architects suffering with our structures because a building is a joke compared with a ship or a spaceship, right? And then this kind of energy, strain energy theories and tools are used every day by those engineers. There's one example. We know, because we studied, right? And we will tell, if we have time today, I don't know, because I wanted to go fast, but we're not going fast. So we know that we have the bracings to absorb horizontal shakes, right? They should converge to one point to have a very rigid connection. This is a basic principle when you make a truss, right? But these are in purpose eccentric. So under huge loads, that will create eccentricity, and it will go, this point will go beyond the elastic limit. Will work in plastic limit. And we know that will absorb a lot of energy. So that energy will allow the building to stand that sudden shock. We have to be careful because this may be a one-time event. The building may not collapse, but the structure may be permanently damaged. But we are speaking of very unique events and safety of people, right? We consider buildings like semiconductor in this case. But even it can be calculated in a way that the structure is not destroyed even after a big event, right? Can be used. But this is a great, great feature. In some cases, we use dampers, which absorb energy as more mechanical elements, but it's a very simple, very cheap way to achieve it. Another example is the crack control, right? We don't need to go into it, but the theory allows us to calculate how deep a crack is critical, so we can consider it okay. Usually, airplanes, ships have cracks, so they are calculated with a acceptable crack, which can be inspected by the eye. And if it goes beyond that, we know it needs repair. If the cracks which are acceptable are very microscopic, it will be very hard to inspect. I didn't see this applied in buildings, but probably may have its application in large structures like super high skyscrapers. But now I'm speaking just as an academic. Right? I never made any building or collaborating a building beyond 20 floors. Right? So I saw the construction of super tall buildings, but I don't know. Really, I don't know beyond the theory. So with all this energy, this is second activity, right? We have two beams, one normal reinforced concrete beam and one pre-stressed concrete beam, which we'll comment later. In the case they collapse, which collapse will be more catastrophic? This is a straight application of what we said just a minute ago, right? So we have just the everyday normal reinforced concrete and the pre-stressed beam, and they collapse. We met in the laboratory, making an experiment, and when we break elements in laboratory, we have to be careful with it, because that collapse may be too dangerous, maybe harmful, right? So which will be more catastrophic? Well, just write it. I will not say more. In the previous one, which were numbers, we commented here, but here I will let you think about it. And you don't need even 1 minute. As I said, I could see in your faces that you knew the reply, which is good. For those online, of course you do, right? Let's go on. And now we are today. This is what we have planned to see. No, this is still yesterday. We studied yesterday, sorry. Loads. Well, loads is very easy. So I have the information here, but really there's not much to explain. So I will comment just a couple of things. And that's what means by loads, right? Extreme loads in a building. So we know the dead static loads. Dead loads are the building itself, important. Sometimes the engineers forget to study them. Then we have dynamic loads that in buildings we use very seldom, even for parkings and so on. It's more for bridges and so on. But thermal, underground water, and wind are stresses we know, and they're tabulated, and we know how to deal with them, right? Wind loads, for example, important thing of wind loads, which we often forget, is that if the wind comes from one side, there's negative pressure on the other side. And we have full curtain walls and facades that disappear from the building. So careful with this negative pressure, because it is very easy to overlook, because sometimes it is the guy of the windows doing it, and he has not any kind of concept about structure, right? So we have to be sure it is dealt with, because one full curtain wall falling down is quite embarrassing and quite hard to repair. So this is taken from the Salvatori book. I commented at the beginning, very great book to have full understanding of the structures for architects. Wind loads is one dynamic load. And I took this drawing because it is great to understand how the structure works, right? If you visualize the formations, this is just concentrated loads. So we know moments will be straight lines. And apart from conventions, I'm used to put a positive moment where the bending happens, right? This is inflection point and then another one. So this is moment for that element, right? And this moment will be like this, right? So putting always the positive moment on the bent area is very graphic, very easy to see. And the deformation will be parabola, right? Probably second or third degree parabola, because the integral of that line. Seismic load is a bit more tricky, because if wind, we don't know the direction, the duration, and the way it comes, right? Earthquakes are even more tricky. They can move top to bottom, side to side, can be revolving, and maybe long, short. But what we saw, especially in tall buildings, which is effective, is the vibration periods, right? I studied that. We had those mathematics in 5th year at university. And I passed the exam, and I forgot afterwards, never used, but it's vibrational mathematics, which are kind of tricky, complex, allow us to have those dampers, those counterweights to make the building just not be shaken with the, just to absorb, to dampen these vibrations from the ground, right? And this is why big buildings have this kind of huge weight on the top, just to act as a counterweight. So this is this kind of mathematics. More important, especially in big spans, what we commented, thermal loads will make elements deform quite a lot. Usually we have a limit of 40 meters, right? Or 30 meters, not to consider thermal load. So if buildings are smaller than that, probably it is okay. But in very slim and light structures, as in roofs, maybe we have to consider them, right? It's additional stress. With cold, they will contract. With heat, they will expand. And we have bolted, welded joints, which may be suffering from those expansions. And most important is asymmetrical or unsymmetrical loads. We calculate always symmetrical structures as symmetrical. And usually they die, they collapse because of this asymmetrical thing. Imagine we have sunshine in the morning and the wind from the other side, west wind. We have an accumulation of asymmetrical loads which may make the structure collapse. Maybe this is behind Malaysia and other structures collapsed we saw before. Well, this is in very big buildings. Of course, you will have more expansion when it is exposed to the sunshine and less in the core because it is not exposed. It has heat air conditioned. In very tall towers, right? This was speaking of the 100 floor, well, of 40 floors. Maybe the engineers have to consider it because it creates additional stresses, which may also create some problems in the structure. And also, this will go to the today's lecture. This is still yesterday. The settlement in the ground, which may happen, should not happen, but sometimes it happens, may create stresses which are not considered in the beginning. Actually, you can calculate it, but we have to plan, build in a way that this does not happen, right? So it's why the knowledge of the ground is important to avoid these problems and to have buildings healthy and so on. So for very rough estimations, a very generic rule of thumb, this is speaking of foundation buildings weight, is usually one building, usual building, offices, housing is about 600 kilograms per square meter, right? That includes dead load and used load. This is very standard. I have seen it in Europe, in the States, and roughly the same. In public buildings, like movie theaters and so on, you may go higher because you have more concentration, right? But that lets you know how much one building weighs, which is cool. And that's the title of one documentary on Norman Foster, right? How much does your building weigh, Mr. Foster? This was a question that Buckminster Fuller said to Foster. So he said, what, my building weight? He was totally shocked. That demonstrates how genius is Fuller, right? He's able to knock down Foster, which is not easy. And then he made a full documentary. So you know how much one building weighs in general. There's a very rough estimation, and with that we can make some approximation. So an example of load estimation. This is a project I was involved a few years ago. This is in Korea. Just one stair. You can see the diagram, right? It is just fixed in 2 points with 2 columns, very simple. Of course, this goes to the slab and this goes to the floor. This is simulation by the engineers. And on the left, I just did my own fast 30 calculations by hand. You can see there's just rough numbers, nothing, and compared to them. And I was shocked because you see there is almost no stress on the columns, right? It's in the cantilevers, that's the critical points. Why does it happen? So they made an estimation of load totally symmetrical. And I said, that's dangerous. Usually nothing happens because it's oversized, but this is an office building, something may happen. This is how, let's see the graph. This is how it is calculated, right? Symmetrical load is very easy and very forgiving with the column. But what happens if you have people going to one side for whichever reason, which may happen somebody totally unthought. So I was sorry because I was working with entire companies and the engineers were kind of opposite to it, but I was telling, come on, this may happen. And it is just a calculation time. In terms of construction, doesn't change so much, right? Another example, well, we can speak of collapses, and actually I did not prepare yet because we are so entertained with those kind of logistics. But we have two collapses recently, right? iPark, which is hard for me because all information is in Korean, but I think it's interesting to analyze it. And before that, we have Parkside apartments in Florida. That's very catastrophic. So we may speak about them. This is Older, a New World Hotel in Singapore. Normal building, 1970s, probably, a computer calculation. The building collapsed, but like that, with people sleeping inside. So there were quite a few casualties there. And the investigation team went through the project and there was nothing wrong. The materials were correct. The construction did not show any problem. This is Singapore. We don't have freezing temperatures. It happened in Gwangju in winter. The calculations were perfect. It's computer calculation. They did perfect. They nailed everything by the decimal. So they had to go several times. And then they discovered with panic that the engineers forgot to introduce the dead loads of the building. They did a very complete study of the overloads, the living loads and the wind and the spread and everything else, but they forgot the weight of the building itself. That means the structure was for years working at twice the stress it was calculated with. And the building was cracking for years, and the management just repaired the cracks right, until it collapsed. So this is why I insist so much on cracks. To get this familiar, many cracks are totally innocuous, have no problem at all, but structural cracks, you have to have very clear in your mind those which are really worrying, right? And one column with cracks is always a problem, whichever cracks the column has, right? So call one expert, a real expert, right? Somebody who really knows, not those who say they know. Being the president of a big company doesn't mean you know a lot. Right? Go to the experts and make sure they know what they are doing and they give you the right information. So we commented yesterday, human error makes computers useless. And this is where probably if they had an engineer, old school engineer, and had made it like I did with, well, old school, right? Very old school. If they did some kind of rough calculation by hand, they could spot the mistake right away because it's very easy to spot. Right? And this is Pamplona in Spain. You know, the famous street where people run in front of the bulls. This didn't happen for 2 years, but this image is the nightmare of any engineer. You never crowd a balcony, right? When we calculate, it's like 2 or 3 people per balcony maximum. But those guys charge the balcony for people pay to use it. So the more people, the more money you get. So engineers in that town are very, really oversizing things. Why I show this? Because no matter how correct, how perfect we are in our estimation, we don't know how people use buildings, right? We don't know. And one famous collapse, 1996 maybe, Sampung department store. It had many, many errors, but one was crazy use of overloads in the roof, right? Which engineers never imagined could happen. So it's one of the triggering elements. You have to be aware of that. And something is beyond the engineer, so you cannot go to the extreme cases. But then is where we need basic common sense in building managers, especially when you're manager of a department store, a big office building, campus, stadium, and so on. And this is the last slide of yesterday. We're today, and are we going to finish? Oh, but are we going too fast? You can say yes if you think. Okay. This is the last slide of yesterday. When we calculate, this is the possible combinations in a 2-span beam. Like a very simple calculation. And you see we have like a 4 possibilities, and we have to calculate all 4. Imagine this building, right? How many spans do we have and how many floors? How many combinations? So there's no way we can calculate all possible combinations, right? Some of them are not critical, but some might be. We might use some classrooms. Imagine everybody goes to this side of the building, right? And the other side is totally empty, right? Then the structure may suffer a little bit, may not behave as we thought. So that means even with the best simulation program, we have to simplify. We have to make compromises. And we just make a bet of what is most probable to happen, right? We're always thinking the probabilities. No matter how much better we calculate now, we can fine tune, we can reduce, we can be more efficient, but still we have a limitation in that point, right? So structures where the computers are much slimmer, we can reduce the margins, but this point beyond which we cannot go because we don't know the future. We don't know what people do with buildings. We never know. It's very philosophical. Actually, it's so very true, right? So much we don't know. So we are working on guesses, right? Good guesses, very educated, very safe, but we are never 100% sure, right? We know the strength of a structure when it collapses. It is the same as the life of one person. You go to the doctor, I go to the doctor, right? I have to go every year to the hospital here, the best in the world, in their own opinion. And they tell me, okay, this is good, this is okay, you have to be careful with it. But if I ask, doctor, will I die tomorrow? Will be alive tomorrow, next year? Well, it looks like you will, but nobody will tell you, right? Buildings a little bit in that order, right? Of course, we have to be a bit more confident, right? If clients say, this building will last 10 years, if you doubt, your client will be in panic, right? So, okay, surely no problem. If used and maintained correctly and no disaster happens, this building should be correct to go, right? But you cannot give your word for hundreds of people or dozens of people who worked in the construction. Maybe things happen which are beyond their control. So if everything was okay, the building will last, right? And actually collapses are very rare. If we consider all the buildings in the world, the collapses we have, it's ridiculous. But still collapses are something we should avoid, right? Are embarrassing. Again, remember, asymmetrical loads are more critical. So if you have to choose, we go to the asymmetrical loads, right? And then we go to today. The ground, we commented, unless your building is like this, right? We need to consider the ground. Ground is half the problem. So let's spend a few minutes about it, at least to be familiar with what we have. This is familiar. I don't need to insist because it's explained twice, right? But let's go back to Newton. Let's think on a plot of the city, a cube of ground. Actually, there are action and reaction everywhere in all phases, right? So what happens when you excavate? We lost that balancing point, right? What happens? Mystery. Sometimes we are lucky. Most often, if you like that, it will collapse, right? And this is something we do every day to make buildings. So just to give you the idea of how much an excavation has to do with the stability of the ground, I have a small question for you. And this you need 1 minute because it's just a very simple calculation. Imagine we have a building with a weight, we commented, the 600 kilograms per square meter, right? We excavate 10 meters. Remember from materials that the earth ground is about 2 tons per cubic meter, right? So 1.6, let's say 2 tons to have round numbers. This is the density of the earth. Normal earth ground would be about 1.6 or so, right? But say 2. So if you excavate 10 meters, we are taking out of this bottom like 20 tons each square meter, right? This used to have 20 tons per square meter. Now it doesn't have. So the ground should push out because it's not any weight anymore. The point is how many floors So we have 3 basement floors, which is about 10 meters, right? How many floors you have to build to keep the original 20 tons per square meter? Just a fast calculation. 10 meters excavation is like the smallest excavation you will see in Seoul. Usually we have like a 20, 30 meters excavation. That creates an imbalance in the earth, right? So how much do we need to build to have this ground in balance totally? Very fast calculation. Actually, this is a problem for middle school, I think, or even elementary school. It's just a division. D, you can think yourself, you don't need to put the balance. It is important, I say you from now. But how many floors do we need to keep that initial strength? Horizontal strength, okay, we support with the building beams and columns and with some temporary elements, right? It is important because it's a huge pressure on the sides. And this is one of the difficulties of those excavations. There's a lot of numbers and money going there. But the bottom, right? What happens in the bottom? Anybody did already? 600 kilograms, like 0.6 tons per square meter, right? So you have to reach the 20, just a proportion. 20 divided by 0.6. Anybody who has a steel brain intact? How many floors? Hey, don't be shy. Come on, this is mathematics. What will you do when we put this in the exam? Well, it's about the 30 somewhat, right? 30 somewhat floors of a user building. Am I right? Yes. So this is how you find the balance, right? If you don't put a building, it will collapse and go up. Well, might be. It happens sometimes, right? Depends on the ground nature and what happens in the underground. And I put this number because my hometown, Madrid, which is a city of sand, soil, by tradition, basements are limited to 10 meters, right? Because it's more or less the maximum you will build over that. Usually we make nothing more than 10 floors, but there will be kind of a balance there. It will not be a big stress. The good thing is that the soil moves very slowly, right? And the reaction is like really slow. So you may have time to build in the meantime, but in some kind of grounds that may be critical. This is a new engineering building excavation. And this is made in rock, but you can see all this, right? It's kind of a projected concrete with anchors to the rock, so it doesn't collapse. You don't take chances, right? And you see there is a groundwater. So this is another thing. Good water giving pressure, and still now we have groundwater. So we have pumps every day and every night pumping water out of the mountain. Don't ask me how much energy. And collapses are natural, normal, right? This happened a few years ago in Chile. They had some slurry walls, but just without any big loads, just a street, it collapsed. That happens even in the best families with the best engineers, right? And one more, this is 2 years later, this happened in Italy, in Rome. And this is quite correct. It was kind of a set of piles, but they were just the piles themselves. So the concrete was not able to support all that overweight. Maybe with some kind of groundwater, some rain, I don't know the cause, but this is quite embarrassing, especially having built this nearby, because this collapse affects the foundation of those buildings. That capacity affects the ground below that. So this is quite critical. Very careful when you make basements, but especially with nearby buildings or with the streets. Well, this is quite famous. Let's go. This was caused by a building. You can see the piles, and they were excavating one parking lot. And they were putting the land of excavation on one of the sides. And at some point, that overload to make the building just totally tumble down, right, on the side. And again, this is quite embarrassing because not only you have to face a lot of court suits, but it goes all around the world, so everybody knows about what happened. So one thing which is important is to know the nature of the underground. For the excavation, I hope I made clear how important it is to consider excavations, and also for the foundation design, right? How we do not underground? So there is cartography. The nature of the grounds is important. I think this is Seoul. This is the best I could find. We have areas which are like a really granite, very, very strong, but we have a big area, right? The whole area, which is the river side, is very soft, very tricky, and very full of water ground, as it happens with all riverbeds, right? And most cities have a river nearby. So this is why it is hard to work in that area. This is why Gangnam is not the best place to build high-rise. This is why they have so many problems. So this gives you a rough idea of the nature of the ground you might find. But usually you make surveys. And there's like two kinds of surveys, just to be familiar. One, very easy, very cheap, we call standard penetration test, or SPT. This is just a very tiny drilling machine, right? Which just punches the floor, but the number of times they need to go 20 centimeters, they make a graph and they tell you how strong or how compact the floor is. So you may have an idea of how it will perform mechanically, and you can calculate your foundations. It is fast, immediate, it is very cheap, anybody can do it. And this machine is small, so you can make even in the basement of one building. If you have to make some renovation, make it. We could have in this building. Imagine we can put more, excavate more underground floors. So it is very practical, but it's totally blind. We have no idea on the nature of the ground. We may know where is the water, because the point will be wet at some point, so you may find the water, but that's all, right? And this is the report you get. It's like a table. This is depth, right? This is meters. So this is done until probably 19, 20 meters. And this is 1 point every 20 centimeters. This kind of a standard. This is why standard penetration test. So you see the strength, not surprisingly, as you go down, the pressure is larger, so the rain is more compact. But you see, something unexpected happens. At some point, we have very weak soil. That happens. This is okay. We may have weak elements, and then after probably 14 meters or so, it becomes really, really strong. Not as strong that it cannot continue penetrating, but much, much stronger. So in this case, probably we would think the foundation should be around 14, 15 meters deep, right? And that gives a lot of information. But we don't know. This is rock. This was clay. We don't know, right? So to have a better knowledge, we have the survey with we call the bore, right? It's not that it's boring. I thought it's not boring, but it's called bore, right? It's kind of a drill in which you take samples. And this is expensive. And you need to have an expert. And the machines are much bigger, right? So it takes much more cost. And you need experts operating the machines and supervising the work, because the samples must be taken very carefully. So we do not manipulate them. We don't change the properties. So they can go to the laboratory and they can make tests with them. This is great because we know the whole sections, right? This is how we do. So you put in boxes the samples and they go to the laboratory. So you know exactly what you have. And this can drill rocks, right? It's very powerful drill. This is great, but it's much slower, much more expensive. And then laboratory work might take weeks because they need to, you know, the experiments with the earth, you get long-term and compressibility and things like that. The experiments are very, very time-consuming. And this is the kind of report. This is much more complex, but you have the depth, right? You have the description of the soil you have. You have the thickness of each kind of a layer. Some kind of symbolism for you to have it more visually clear. Then the samples where they are taken, and then you can do standard penetration tests at the same time, right? And with that, plus the laboratory report, you can have a very accurate idea on how the ground works. You may have also samples of water taken to the laboratory to see if they will be aggressive against concrete and so on. So you get a lot of information. What do we do usually? If we have a big plot, right, we try to plan 3 points which we think critical for this survey, and then additional small points with the standard penetration test, right, to see if there is anything special. Because sometimes we are unlucky, and those 3 are totally perfect, and we have an underground river just between them. That happened to me once, right? And you know when you excavate. So this is great. And this is the kind of report you get, right? The nature and also the mechanical characteristics. Probably this is what you need to know better. Layering water level is important because then you can preview how to make excavation and how to make those basement walls later. And then, you know, this is statistic. This is like sim points. We will know the total reality when we excavate. So we have to be ready to have some unthought findings, right? Right. So the space in between, we just guess and we hope they are okay. So let's so much for the ground, not much, but surely those surveys are very important. You should be familiar with them. And even if you do not engineer the structure and the excavation and so on, you should be familiar because you already know what you can expect, right? And the most important, even if I say the general survey is a bit more expensive with the samples, it is enormously cheap compared with the cost of the foundation, and even cheaper if you have to make repairs later. And I cannot understand why many clients refuse to do it, thinking every building around is healthy. We have rock here, right? Well, rock, we have water, we have cracks, and we have, we don't know. So I wouldn't start any construction without this kind of study. And in most of Europe, it is illegal to build without this kind of report before, right? Because it is just common sense. Let's go into columns and walls, which makes for this great architecture. You can see now that we have those beams. These are the beams which, if they collapse, they will collapse by shear stress, right? Not by moment. So something in columns, in this kind of construction, the stability is one basic point. This is taken from one of the reference books. So we usually consider the load in the center. So the ground or the support of the column below is giving you totally regular reply. This is the ideal. This is what you should aim for. But as the load goes to one side, to have a balance, right? The reply, the reaction has to change, right, to counterbalance. And since if the lower part is uniform, this will be kind of linear, right, equation. In clay sand, this could be parabolic, but well, we will not speak about it. And actually, the peak is realistic, is kind of a parabolic line. But okay, the point here is that at some point the stability is compromised, and this is for one column or for one full tower, right? And this eccentricity is the same as having a moment, right? This one for this distance is a moment, right? So sometimes having a moment is calculated or modelized as kind of eccentricity. Is the same thing. And also, this can be the result not of a moment, but of our horizontal load, right? So it's probably the same, right? So you can modelize the wind stress, horizontal stress, or moments as eccentricity. The important thing is how it affects the lower floor or the support. So there's a moment in which you start having negative stress and the element collapses, right? This is basic stability for one column or for one building. And we have a famous building in San Francisco, Millennium Tower, leaning, and the engineers being really worried because it's already 60 centimeters leaning because of this kind of stability problem. Right? The super slim towers are tricky, right? Even you can see them in New York and San Francisco and those places. We are far from having them perfect. But this is very simple calculation people did for ages. I will give you an example. So this is the same, but telling you how the weight will help having the balance and the structure. This is the principle of the Gothic cathedrals, right? The pinnacles, which give more load, so they have a balanced thing. But this is a great example. Our Uri Gaudi, right? Gaudi calculated all his buildings himself without computers. Before computers, there was a choice to doing this graphically, and you can calculate reinforced concrete structures graphically, right? It's so fun. Well, not fun, but so much better than making numbers in a computer. So Gaudi structures are very rational and very much based on mechanics. And this is taken from his drawings for application for the permission, because come on, you see his buildings, they will collapse. So thin, so tall, so, and then say, demonstrate it will start. So you say, this is the composition of loads, and you see they are always in the right place. This is just application of the principle we saw. He would make models in laboratory for the catenaries and then use them for building. But the point here is that an architect we admire, I think, who is thought as a genius, imaginative, and so on, he was the hell of an engineer. Actually, at university, he was among best in mathematics and physics, right? So he was able, we may say, okay, 100 years ago, physics were much easier. But we just saw that's the same physics which today, right? Except for that strain energy, which is some new thing, but same physics, right? And this is just stability, that's plain stability. Then for the stress, if you calculate the stress in that stone, you will see that it is by far safe, right? The problem here was the stability. All these more cases, right? Those lines, how the weight is analyzed to make sure in the end it goes to the foundation and the structure is stable. Right? This is purely graphic calculation. That composition of forces, those parallelograms you do sometimes in structural mechanics. And as we said, the models for catenaries, so you have the maximum efficiency in the shape of the walls. So you have almost no centricity. The materials will be 100%, and you have, this is Sagrada Familia, right? So really looking down a set of chains of ropes falling by gravity. So this is repetition. Longitudinal stress is very easy to understand. I will not go into it, but it's important to know the buckling. In those stone buildings, buckling probably Gaudi is a bit in the limit, but still not so much. The stronger materials we have, the more tendency they will have to buckle, to bend, even if they are not in the maximum stress, right? We know by experience it happens. And that happens, actually, it's more acute in steel, because steel is very strong. So sometimes we have to dimension based on avoiding buckling than on the strength itself. We are lucky because it is very easy to calculate, and usually if we are familiar with the proportions, it's okay, like 1/20th of the height usually is safe in most cases. But this is a famous graphic by Fuller, right? Which it says, if we have an element in compression, it may collapse in two ways, the squash or the banana. Squash is a typical collapse of the fragile elements, the real compression collapse. The banana is the one in which the element doesn't break, but just bends because it's too strong and too slim. And that's great. So concrete usually collapses as the squash. And concrete is reinforced concrete has a steel. So steel is given the shape of a squash, but it's clearly individual bananas, right? The steel does not break, just bend. But the concrete breaks. It is interesting, the point, because it happens in the top and the bottom line. So probably the collapse had more things there. But obviously, as we said, as we have pressure, the element expands to the sides, and then we have those vertical cracks and breaks like the squash, right? So when you have vertical cracks in one column, just run, because that means near collapse. You have to be sure this is really the column, not some kind of ledger they put around the column. It happens sometimes, right? Sometimes we have brick around and the brick breaks, but the column is healthy. But horizontal cracks in one column is like the most critical of the collapses, because that means failure by compression. And in this case, the building survives because you have walls and other elements which collaborate, but sometimes the building may collapse. Right. And when the columns are very slim, we have the buckling, and eventually it may break to the breaking, right? But the buckling is the problem. So this is very thick column. So with this proportion, very suddenly we have buckling. This is very extreme pressure, but you see, it's very hard to make it break. To find the crack, still you have to really apply a huge pressure in this case. But there's an experiment we did in materials a few years ago. This is just a spaghetti. And it's very easy to break. This is what I can hold in my hand. You see how it bends, right? So this is very long and it cracks. And then the shorter, it is harder. You can see it is still punching my fingers, but still bends and still cracks. But there's a point, there's no way to break it. Right? We did in class, and people would literally stand on it to break it. Like, that tells you how strong a spaghetti is, right? People had to put the full weight of their body in that thin element. And this is interesting because telling, if we make the dimensions, we have a ratio of 1 to 9, which curiously is the classical proportion of classical columns, 1 to 8, 1 to 10, right? And we are on time almost. Okay. So this is interesting. And this gives you the idea of proportion in a fragile element as concrete, stone, brick. Typical proportion, 1 to 8 to 1 to 10, right? And you're sure that in general it will work. Of course, you can make the calculations and make it slimmer. So this is the calculation. I will not list it because it's very easy. This is thanks to, I think it was Euler or some of those smart guys. If you want to make very slim columns, you have two strategies. Put many, so they have very small stress, right? Or reduce the length by putting ties, right? And just be aware that buckling happens in any compressed elements. And very long and slim beams, the top part is compressed. So they have also the buckling, right? This is the problem we have. This way we have a horizontal ties to reduce this length or make stronger beams, right? So buckling happens in any slim compressed element. And this is the same problem. And we are almost finished, but I don't want to go beyond the class. So the damen, beam and post and trusses is important. I think we left one more question. I don't remember. Question 4. This is my favorite. Okay, let's do it. So next week, right? So we are almost on time, which is amazing because we did 1.5 class in one time. I hope it was not too fast. I can see half your face, which is great. In the Zoom, I cannot see anything, right? But the half face, I cannot say if it is joy or panic. It's kind of, it's hard to distinguish the expression. But again, if you think we were too fast, just tell me, right? And I will try to slow down. If you think we were not clear in some concepts, let me know. I will see what is clear or not in the activities. So the first assignment we will start next week. We said this every 2 weeks, but actually had only 1 week of real contents, right? So, and last year we did some kind of a quiz online. But I will try to find something which is a bit more motivating, funnier, or assignment like. For next week, just please go back to your notes. I think the lecture should be online, the handout, about noon. If Blackboard works well. You will have a video as soon as I can upload it. Yesterday's video is online, but it was so bad. I gave a link in Blackboard to last year's, which is almost the same class. And actually, I elaborated more at some point. So if you don't have anything better to do, you can look at it. Right? There are better movies in YouTube. Okay, this is our job. So let's end here. So people online have time to upload things. Write your final comments if you have any. Actually, always the best of the activities, your questions, comments, complaints, suggestions. And I will make a new survey because we don't have official note from the school about next week. We know that officially week 1 and 2 were advised to be online, so with something in between. I already said my intentions to keep the dual sessions. It's not easy, as you see, but kind of works. Now. Yeah. And probably the sound is not terrible. The people online can say, and I will see the video myself. But I will make a survey to know what happens, because ideally we should have most of the class in class. So you can say what you think better. So those who are offline, you don't need to upload the sheets, just keep them. So we will keep the analog system to the end, right? Actually, I have the sheets from yesterday. If you are here, you can collect them. If not, just as you finish, you can say goodbye in the chat, upload, tell me if the link does not work. Probably the link for uploading works today. But for those in class, just submit the sheet. It's so much easier, so much faster. You can scribble on the sheet, you can bend it, you can make drawings, you can doodle, and then you have it back. So let's finish here. Thank you so much for attending, and see you next.